With Neptune raising worries among researchers and space fans, the same famous specialists, including Neil deGrasse Tyson and Michio Kaku, have sounded cautions about the possible outcomes of this heavenly conflict. Yet, how did Pluto end up on an impact course with its far-off neighbor, and what could this infinite crash mean for us here on the planet? How about we investigate this unfurling event? Once thought to be an undeniable planet, Pluto was subsequently renamed a dwarf planet because of its unique orbit. In spite of this transformation, it continues to enthrall and draw in stargazers. Ongoing forecasts from unmistakable researchers highlight a stressing proximity between Pluto's path and that of Neptune. These specialists alert against a likely crash between the two planets, representing a critical danger to Earth. Pluto's venture around the Sun is marked by its unmatched attributes within our planetary system. Its orbit ranges broadly over 248 years, and since its discovery in 1930, Pluto still hasn't completed a full revolution, adding to its intrigue. A notable feature of Pluto's orbit is its crossing point with Neptune's path. For roughly 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, resisting assumptions based on their respective positions in the solar system. So why hasn't an impact occurred between Pluto and Neptune? The explanation lies in the gravitational impacts applied by different planets. The assessment of Pluto's orbit initiated soon after its discovery, presenting a perplexing challenge for stargazers. In contrast to most of the planets, whose orbits adjust somewhat near the ecliptic plane, Pluto's distinct features include a steep inclination and an eccentric shape. The mystery deepens with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amid these complexities serves as proof of the intricacies inherent in space mechanics. The three-body problem in space involves understanding the movement and gravitational interactions among three heavenly bodies, like Pluto, Neptune, and the Sun. This problem clarifies the complicated exchange of their paths and gravitational forces. Terms like asynchronous libration, apsidal libration, and VZL oscillation contribute to unraveling this cosmic riddle. Astrophysicists affirm that asynchronous libration, responsible for keeping planets in their orbits, plays a fundamental role in the context of Pluto and Neptune. This term means that when Pluto crosses Neptune's orbit, it is situated at least 90 degrees away from Neptune, vital for stalling potential crashes. Apsidal libration ensures that when Pluto approaches Neptune or other giant planets, it is aligned above their orbital plane, providing an extra layer of protection against collisions. The VZL oscillation explains why Pluto's orbit around the Sun appears erratic but remains smooth over time despite apparent irregularities. Mathematical simulations in the late 1980s revealed that notwithstanding steady properties, Pluto's orbit is, in fact, chaotic, with minor initial deviations leading to massive differences over millions of years. However, Pluto's unique orbit maintains stability over extraordinarily long timescales, keeping chaos in check. Ongoing computer tests have improved our understanding of how giant planets like Neptune, Jupiter, and Saturn impact Pluto's orbit around the Sun-Neptune's gravitational relationship with Pluto. Completing 3 orbits for every 2 of Pluto adds to the stability of Pluto's path. Jupiter's tremendous gravity also exerts a significant influence, while Saturn's effect, though more modest, plays a part as well. Through thorough studies, researchers have shown that the combined impacts of Neptune, Jupiter, and Saturn ensure the safe and stable evolution of Pluto in space for billions of years. These phenomena are fundamental for maintaining the order and consistency of heavenly movements in the universe. Without these components, the solar system would be prone to greater chaos and eccentricity, potentially leading to crashes or ejections from stable paths and causing progressively expanding influences on other celestial bodies. Understanding Pluto's orbit is especially essential in discussions about a potential impact with Neptune in the future. This knowledge provides a clearer comprehension of the unique nature of the nearby planetary system. Pluto's case highlights how seemingly unstable orbits can achieve harmony through the complicated interaction of gravitational forces and orbital mechanics. Constant observation and investigation of these phenomena are crucial for acquiring a better understanding of our position in the universe. Exploring the depths of space frequently reveals the eccentric nature of celestial bodies. Moreover, Pluto's orbit serves as a prime illustration of this unconventionality. The concept of orbital chaos distinctly demonstrates the delicate reliance of a celestial body's path on its initial conditions, as exhibited in Pluto's case. Even slight variations in a planet's position or speed can significantly alter its long-term orbit. Programmatic simulations have been instrumental in aiding researchers to understand how Pluto moves in space. By making small changes in these simulations, astronomers can see how minor adjustments can have a profound impact on Pluto's trajectory. In the late 1980s, these simulations uncovered an intriguing aspect of Pluto's path. Despite features like asynchronous libration and apsidal libration contributing to its stability, Pluto's orbit can still exhibit chaos. Even a small initial difference in Pluto's position or speed can lead to massive changes in its path over many years. Nevertheless, this inherent chaos maintains Pluto's orbit in a stable manner over an extraordinarily long time scale, extending over billions of years. This suggests that beneath its seemingly sporadic appearance, Pluto's journey around the Sun follows an organized order, anticipating grandiose events. Particularly with planets like Pluto that have unusual orbits, the intrinsic unusualness of these systems makes long-term predictions uncertain. Mathematical simulations help us understand and anticipate the future paths of celestial bodies. However, they also reveal the limits of our predictive capabilities. These models heavily rely on accurate initial conditions and reproduce complex interactions. Even a small mistake can lead to significantly different outcomes, making precise forecasts difficult. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our continuously limited knowledge. The vastness of interstellar distances and the scarcity of planets in open space serve as obstacles against frequent impacts. Furthermore, rogue planets are relatively rare compared to the number of stars and planets in stable orbits, making such events even more unlikely. Understanding the gravitational effects of giant planets on Pluto's orbit provides important insights into the broader dynamics of the nearby planetary system. It illustrates how each planet's presence and position can influence the stability and trajectory of different bodies within the system. In spite of these complex forces, significant astrophysicists express concerns about a possible impact between Pluto and Neptune. This raises questions about why such an impact, which seems far-fetched given these intricate elements, is now a subject of concern. Neil deGrasse Tyson, a notable astrophysicist, offers an extraordinary perspective on the mysteries of our solar system, especially regarding Pluto. Tyson, popular for renaming Pluto as a dwarf planet rather than a major planet, shares insightful thoughts on how our understanding of celestial mechanics is continuously evolving. He sees Pluto's renaming not as a downgrade but rather as a fundamental acknowledgement of our expanding knowledge about the various objects orbiting the Sun. His approach to celestial mechanics involves constant learning and transformation, viewing the complexities of orbits like Pluto's as a reminder of how much more there is to discover in space. Tyson believes that the allure of these questions is what makes astronomy so captivating. Moreover, he recognizes how space-related events and discoveries influence public interest in space science. He thinks events like Pluto's renaming and its surprising orbit present opportunities to capture the public's imagination and interest in the universe. By discussing the dynamic and sometimes bizarre aspects of celestial mechanics, Tyson aims to cultivate a deeper understanding and appreciation of the cosmos. Neil deGrasse Tyson opens a window for the general public to wonder at the marvels and mysteries of the universe. Working alongside other researchers, Tyson actively alerts the public about the possible risks of Pluto's erratic orbit. After extensive study of Pluto, he has raised concerns that the three-body problem could pose a genuine danger, suggesting that a collision with Neptune is long overdue. Furthermore, Tyson emphasizes how such a crash could disrupt the balance of the universe and lead to catastrophic outcomes extending to Earth. An impact between Pluto and Neptune would be an extraordinary and disastrous event in our nearby planetary system. This collision would release a massive amount of energy, potentially shattering Pluto due to its smaller size and icy composition. Debris from the impact could disperse across the solar system, presenting potential threats to other planets and their moons. For Neptune, Such an impact could possibly alter its climate and orbit, depending on the specific details of the collision. Michio Kaku, a notable theoretical physicist recognized for his work in string theory and science communication, offers an interesting perspective on this situation. His views on the future of space exploration and the interplay between celestial mechanics and theoretical physics provide profound insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, according to Kaku, can offer critical insights for future space missions. This knowledge can aid in navigating the solar system more effectively, anticipating potential dangers, and planning missions to the outer reaches of our planetary system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to investigate other celestial bodies, providing a framework for approaching and understanding distant worlds. In examining the physics of planets, Kaku often highlights the deep connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, like the gravitational dance between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to fathom these principles at the most fundamental level. He proposes that studying the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the underlying laws of the universe. Like Tyson, Kaku has also addressed the potential impact, relating it to his speculations about the universe. If Pluto and Neptune were to collide, it would be a pivotal event in astronomy, offering a remarkable observational opportunity that could potentially contribute to our understanding of string theory. String theory, a hypothetical framework that replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The crash of such magnitude in the nearby planetary system could generate extreme states of energy and gravity, providing insights into the behavior of fundamental particles and forces under extreme conditions, a key focus in string theory. Moreover, the gravitational waves produced by the collision could provide significant data for testing predictions of string theory related to gravity and spacetime. While the immediate effect on Earth would be negligible due to our distance from the outer nearby planetary system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe as depicted by string theory and other areas of theoretical physics. Pluto's orbit serves as a striking illustration of celestial mechanics, demonstrating both stability and chaos within our nearby planetary system. The unique characteristics of its orbit, affected by the gravitational forces of neighboring planets, especially Neptune, highlight the complex and dynamic nature of space. The universe holds many secrets, and the three-body problem is only one of them. There are other potential disasters that researchers anticipate. While the possibilities of planets colliding in space are very low, they are not entirely inconceivable. The way planetary orbits are affected by various factors, including gravitational interactions, is explained by the three-body problem. In some space systems, like TRAPPIST-1, with 7 Earth-sized planets, gravitational forces create a rhythm brought about by orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, impacts are not currently occurring. Researchers closely monitor these systems to understand how planets affect each other's orbits, especially when they are in close proximity. This information helps us appreciate the evolution of planets in space. Rogue planets drifting through space without orbiting a star introduce an additional unpredictable element. These planets, once part of a star system, can be ejected due to gravitational disturbances or other cosmic events, such as the close passage of another star or dynamic instability in other systems. Over the long haul, these wandering planets can traverse vast distances, potentially reaching areas far from their original location. During their solitary journey, there is a possibility of encountering other star systems. If one of these rogue planets enters another nearby planetary system, there is a slight chance of a collision with a planet in that system. However, given the immense and largely empty nature of space, the probability of a rogue planet directly impacting another planet is extremely low. In conclusion, While the threats of collisions in the cosmos are present, the dynamics of celestial mechanics, as illustrated by Pluto's orbit, suggest a remarkable balance maintained by the gravitational forces at play. Ongoing research and simulations continue to enhance our understanding of these complexities, shedding light on the intricate dance of celestial bodies in our universe. The study of such phenomena not only enriches our knowledge of space, but also inspires future explorations, reminding us of the endless mysteries waiting to be uncovered.